Hey guys, what's up? The transistor bias arrangement we'll study today is common emitter configuration. Common emitter configuration of transistor and its characteristics. We've already known, right? In this configuration, input is applied between base and emitter, and output is obtained from emitter and collector. Because emitter is the common terminal here, so its name goes out to be common emitter configuration, and so input is applied between base and emitter, and output is obtained from emitter and collector. We already know that in a circuit having transistor, input is always forward biased and output is always reverse biased. So know the things I've said if you need to. Here I have listed 2 points which I've mentioned as concepts to remember. You'll just need to understand it, and there is not much to it. Here the external voltage source VBB is used to forward bias the base emitter junction, and external voltage source VCC is used to reverse bias the collector base junction. I'll explain it to you when we encounter the diagram for this common emitter configuration. But for now, just understand this. And one more thing, or one more concept that we should be understanding is, in order to ensure that the collector base junction remains reverse biased, it is necessary that the magnitude or the value of VCC is greater than VBB. So I've written this point over here too. VCC must be greater than VBB. Why is it so? Because in order to ensure that the collector base junction remains reverse biased, it is necessary that the magnitude of VCC is greater than VBB. So here you can see the circuit diagram. Should I explain it to you? Well, let me tell you what things are included in here. Okay, this is base in the middle. This is emitter, and this emitter terminal is common to both base and the collector side, and this is collector. So this tends to be the base emitter loop, and this tends to be the collector emitter loop. But base emitter loop is forward biased, I already mentioned, because in a circuit having transistor, input is always forward biased. So this tends to be the base emitter loop, which is input, and this is forward biased, and this is reverse biased. What else is here? Okay, in the previous video of mine, I've already told that the terminal which is common has no resistor. No resistor should be drawn over there. So here is one resistor for the base, and here is one resistor for the collector. So this is base resistor, and this is collector resistor. What else is there? This is a VBB, which is external voltage source, and this is in the base terminal, and it is in base emitter loop, and emitter is common, so this tends to be VBB. So this is why it is named as VBB. It is external voltage source which is applied in order to make this loop, make the circuit forward biased. And here is VCC, which is also external voltage source, which is inserted in the circuit, or which is provided to the loop in order to make this reverse biased. And in order to make this loop reverse biased, it is necessary that VCC is greater than VBB. That is what the point meant, the point that we've studied earlier. Now what else is here? Okay, there is VBE, which was input voltage, and there is VCE, which was output voltage, because it is on the output side, and this is in the input side. And there is IB, which is input current, and this is IC, which is output current. And if we need to come to the circuit diagram again, we'll come to it. So now let's check the input characteristics. Okay, here's the input characteristics. The CE input characteristics. That means the CE input characteristics, I meant to say the common emitter input characteristics resemble to the family of forward biased diode curve. It is because the base emitter region of the transistor is diode. So, base emitter region of the transistor is diode. That means it is the input side, and it is kind of similar to diode, and we'll see how it resembles to the forward biased diode curve when we have a look at the curve itself. For now, just note down the points if you need to. So here input resistance is equal to the change in input voltage, that is change in VBE, base emitter voltage, divided by input current, that is base current. Here VCE is constant, that is output voltage VCE is kept constant in here. IB decreases as VCE increases for a fixed value of VBE. IB decreases as VCE increases. Here VCE is generally kept constant, but when VCE increases, IB decreases for a fixed value when VBE is kept constant for a fixed value of VBE. So a large value of VCE results in a large reverse bias collector base junction, which widens the depletion region and makes the base smaller. When the base is smaller, there are few recombinations of injected minority carrier, and there is corresponding reduction in the base current. So let me explain it to you. Here is the figure, and you can see the emitter is colored in orange, and this is base, which is blue in color, and this is collector, which is purple in color, and here you can see two bars which are chocolatey in color, that is brown in color, and these are depletion layers. Alright, so a large value in VCE results in a large reverse bias collector base junction, which widens the depletion region. That means these depletion layers are widened. So you can think on your own, when these depletion layers, you can see these depletion layers, when these depletion layers widen, obviously the size of the base will get reduced, right? So when this base will get smaller, there are few recombinations. So you might have known that recombination of carriers occur in base. So there are fewer recombinations than it used to be when these depletion layers get widened. So that is why the recombination current will decrease as well. That means the recombination current, or the base current, you can call it base current or recombination current, but whatever it is, it will get reduced as well. So that is what I meant to say, and if you need to note down this idea, I'll just write it for you. Come on, now let's move into input characteristics. I'll just write it for you. Okay. A large value of VCE, that is collector emitter voltage results in a large reverse bias. Oh, sorry, I made a mistake in the spelling of collector. It's a large reverse bias collector, collector base, what is it? Junction, so which widens the depletion layers, or the depletion region, you can say, or region, and make the base smaller. So when the base is smaller, there are fewer recombinations. There are fewer recombinations than the usual one. There are fewer recombinations. So minority, I'll make it for you. Okay, minority carriers, and there is corresponding reduction in base current, reduction in recombination current, or the base current. So you can note this point down if you need to. Now let's do this by again. Alright, and here is the figure. I'll explain it to you. And this is what the input characteristics curve looks like, and everything that has to be told about it, or every information has already been given to you. You can just tally what I've said with this curve, and you can study the curve on your own. So let's move forward to output characteristics. As we've already known that it is the curve between IC, that is collector current, and collector emitter voltage, we'll just go to the circuit diagram. So this is the output loop, and the output parameters are IC and VCE, as I've already told, and the graph is plotted in between them in order to make the output characteristics curve, and we'll study the output characteristics from that curve itself. Okay, so there are no other parameters that can be used to plot the graph, right? So we need one voltage and we need one current, and these are the things. This VCE is the voltage, output voltage, and IC is the output current. So let's move to that particular slide. There are points down there. Okay, so the collector current IC varies with VCE for VCE between 0 and 1 volt only. After this, collector current become almost constant and independent of VCE. So here is the curve, and you can see there is one point. This is origin, of course, and it is always 0, and this point can be considered as 1. And up to this point, the IC varies with change in VCE. But after this, you can see that there are straight horizontal lines, and there is not much change that can be observed in case of IC, right? With the increase or decrease in VCE. So that is what the point says. And after this, collector current become almost constant and independent of VCE. So independent in the sense that how much you increase or decrease VCE after 1 volt, you won't see any changes in IC, right? So that means that is certainly kind of independent of VCE, because how much you change, how much you decrease or increase the VCE, you will find no change in IC. That means whether there is VCE or not, there is no matter what, it always is constant, because you can see the straight horizontal lines. Okay, so this value of VCE is up to when the collector current reaches or changes with VCE, which is called knee voltage. The transistor is always operated above the knee voltage. You can see after this, it is knee voltage, and now that you can see that okay, there are straight horizontal lines. That means the transistor operates in this region. This is Cardiff region. Well, okay, the above knee voltage collector current is always constant. Above knee voltage, that means I've already told you this point is for knee voltage, and above this, the collector current is always constant. So, well, I think I need to tell you one more thing. That is, however, a small increase in collector current with increase in collector emitter voltage can be observed. Well, the point says that there is no change in collector current after the knee voltage, but however, there is a point where it says, however, a small increase in collector current with increase in collector emitter voltage can be observed, which is caused by the collector depletion layer getting wider and capturing a few more majority carrier before electron-hole combination occur at base. I'm gonna write it down for you again. Okay, however, a small increase in collector current with increase in collector emitter voltage can be observed. We better not write it. Okay, it's caused by the collector depletion layer. collector depletion layer getting wider. There is always mistake. Okay, it is Getting, right? Okay. Wider and capturing a few more majority carrier before electron. I don't know why I always miss this E. Electron hole combination occur at base. Okay. So this is the point for you. Okay, let's do this. Right. So, okay, however, a small increase in collector current with increasing collector emitter voltage, that is VCE, is caused by the collector depletion layer getting wider and capturing a few more majority carrier before the electron hole combination occur at base. So I've got this figure one more time, and you can see the depletion layer in collector, right? So this gets widened. So VC results, a large value in VC results in large reverse bias collector base junction. Okay, so not this point. A small increase in collector current with increase in collector emitter voltage can be observed, which is caused by the collector depletion layer. So this is the collector depletion layer. This is the collector depletion layer, which gets wider, and because this gets wider. Before the recombination occurs in base, few minor majority carriers go over here. So the electron hole combination will not be able to occur at base, and the majority carrier will come to the collector side. And this is what happens when increase in collector emitter voltage is made, and you can observe a small increase in collector current as well. So this is due to this reason why that happens. Okay, I hope you understood it well. Well, this is the output characteristics curve for common emitter configuration of transistor, and this is the output characteristics, and I've explained everything to you. Hope you guys understood it, and hope it helped you to some extent. So if you find it helpful, please consider subscribing. See you in my next video. Till then, have a good day. Goodbye.